Okay, here's our review. So you kind of have a general idea of what's going to be on the test, but I'm going to just talk a few specifics here. Maybe work through a couple of problems. So separation of variables. So let's say I give you this problem. Y prime minus xy plus y is equal to 2y. Okay. So first thing we do in these separation of variable problems is we replace dy y prime with dy dx. And I mean, I guess you could move the variables around and see if you can factor things out even before you do that. So let's just leave it as, well, we can still leave it as dy dx. Okay. Now the rest of it is, if you can combine like terms, then do that. So you can see that if I add this to both sides, that'll disappear and I'll end up with x times y. If I subtract y from both sides, I'll end up with 2y. So what I'm going to do is add xy to both sides. And you'll notice I've got a y here and I've got a y over there, so those actually are like terms, and you do the math. So these go to 0, this goes to 0, and then you get them on the other side. You actually have 2y minus y, which is y. And you have x plus y. So we end up with x times y plus y. The key thing here is that you can factor out the y. You know, if I had something like y, well, let me just do the problem, then I'll explain. Okay, so now we can multiply both sides by dx. Like that. And then if we just divided by this quantity, we'd end up with x over on the left-hand side, which is not good. So you have to find some way of factoring out the x, or y. In this case, it's the y, because it's a common term in both of them. So you get y times x plus 1 times dx. So by doing this factoring, you can separate this variable out from the x quantity. If I had y squared, though, that wouldn't work. You know, it's just, let me just do that. If I had xy plus y squared, and I factored out the y, I'd still have the x and y stuck together. So I wouldn't be able to separate an equation that had something like that. So the one on the test, of course, has to be worked out where this is separable. Okay, at this point, then I can do these divisions. I'm going to divide by y. So I end up with dy over y is equal to x plus 1 times dx. So I have separated them. And on the test, if you do the problem, you should end up with something that is going to be fairly simple. You know, it's either going to be polynomial or it's going to be something that's like a natural log. So in this case, I'd integrate both sides. And the thing about separation of variables is you just integrate each side like you normally would. You don't have to worry about implicitness because everything's in function of y over here and everything's a function of x. So the integral of dy over y is a natural log of the f by y. The integral of this is x squared over 2 plus x, because the integral of x is, if you add 1 to the exponent, which gives you 2 divided by the new exponent. The integral of dx is just x, and then you add this arbitrary constant c onto the end of it. So, if you wanted to solve for y, then you would do this. And the e to the natural log of y is just equal to y, so you end up with that. But I would want you to simplify this where you don't have the constant in the exponent, so we can break this up into two exponential terms using the properties of exponents as far as they're, you know, if you have things added together, you could break it up into e to the x squared times e to the x times e to the c. I've only broken up the constant part so that I can bring that out front, and I can have that. Therefore, the constant's not separate here in the exponent. It's a constant in front. Okay, so there's separation of variables. The second one is if we had this homogeneous differential equation. So we need to convert it so that it is differentiable. So if I had 3x squared, 3xy squared dx plus x cubed plus 2x squared y times dy equals 0. Now it's homogeneous because you can see I've got x times x squared, which again, if I use meters as a unit, I'd end up with meters cubed. Here I'd end up with meters cubed. Here I'd end up with meters cubed. So it is homogeneous. I could also rewrite. If I started out, if I solve for dy dx, I'd get negative 3xy squared divided by x cubed plus 2x squared y. So what I've done is move this to the right-hand side, it becomes negative, and then divide by that, and then divide by dx. So I could have given you a problem like this, but I'm not. I'll give it to you something like that. So what you need to do is use two substitutions that nu is equal to actually y is equal to nu x, and then the derivative dy is equal to nu dx plus x d nu. So those are the substitutions. The rest of it is algebra. So I get 3x from here times y squared times dx plus x cubed plus 2x squared times y, which is nu x, the whole thing times dy. Oh, but dy is, can't just leave dy in there, so I have to put in nu dx plus x d nu, and all equals 0. So y squared becomes this squared, dx stays the same, x cubed stays the same, y becomes nu x, dy becomes nu dx plus x d nu. Now you have to multiply this whole thing out, and you want to order the terms. So here you're going to have 3, and we have x times x squared, so it's going to be x cubed. Then we have nu squared times dx. So that's all this stuff multiplied out and grouped together and ordered. Now the second one, you're going to have to use FOIL. So what we'd end up with is f would be x cubed times nu dx. So that times that. Okay. F first, inner. So the inner part would be 2x squared, actually x cubed, because there's actually, I could reduce this down to x cubed. So that the x cubed, so we get 2x squared times x is x cubed, nu times nu is nu squared, times dx. Okay, so that's the inner. And then you'd have the outer, which would be x cubed times x d nu, so that's going to be x to the 4th d nu. And then finally, last, which would be these two, you'll have 2 times x, 2x cubed, so I've got 2x squared times x, so that's x cubed times x, so that's going to be 2x to the 4th, and then I've got a nu, and then a d nu. So so I'm comparing these two. If you need to write them out, do it. 2x squared times x, that's x cubed, times x again is x to the 4th, nu only have one nu times d nu. That whole thing equals 0. So then you look to see if there's any cases where I can combine like terms. Well, this and that are x cubed nu squared. I think that's it. So we'll get 5 x cubed nu squared dx plus 3 or plus x cubed nu dx plus x to the 4th d nu plus 2x to the 4th nu d nu. Okay, so that's combining like terms. Now you should be able to, you might be able to factor out some things here because there's a common term, and you can see that here. You've got x cubed and you've got x cubed, and you've got x to the 4th and you've got x to the 4th. So the first two terms can, if we factor out x cubed, we get x cubed times 5 nu squared plus nu. So so you get 5 nu squared d, and I've got to put dx on the end here. So you get 5 nu squared dx, and you get nu dx. Okay, the second one you can factor out x to the 4th. That leaves. We're also going to factor out d nu. So you got to have those out of there. So you got d nu. So if you factor out x to the 4th, you're going to have 1 from here, because I factored out both x to the 4th on the front and d nu on the back. So that leaves just 1. And then I have 2 nu, and the d nu is on the back side. So I get 2 nu times d nu. That all equals 0. And now you can see I can do some separating. So what I'm going to do is I'm just going to move things here before I divide anything out. So I'm going to put this one on the left-hand side. I'm going to move the other one to the right-hand side. So we're going to have that with the negative sign. And I'm going to divide by this, and I'm going to divide by that. So divide by x to the 4th, divide by 5 nu squared plus nu. And what that will leave me is with this 1 plus 2 nu times d nu divided by 5 nu squared plus nu is equal to negative x cubed over x to the 4th times dx, which is negative dx over x, because you can simplify that. And that shows actually another thing I could have done earlier is I could have divided everything by x cubed, and I would have done this part earlier. So again, what we do is you start with the original differential equation. Here are your substitutions. You substitute in for y and for dy. You multiply everything out, being very careful of what you're taking everything into account. You combine like terms, which is what I did here. I could have divided out a common factor out of all of these. I could have divided everything by x cubed, which I probably should have done. What that would have done is if I had realized that, then this step would have been there. So if I got rid of either 5 nu squared dx and just nu dx. So if I'd done that, then I wouldn't have this step. But it ends up the same. The same final result is I get 1 plus 2 nu over 5 nu squared plus nu. The whole thing times d nu is equal to negative dx over x. Obviously, if I integrate this, I'd get the natural log of x. This one I'd have to probably think about for a while. Okay, there's going to be an exponential growth problem or decay. So be prepared to do either one, exponential growth or exponential decay. In this case, I have this fish that is not a native fish in the Caribbean, and I'm looking at how fast this thing's growing. Actually, this is a logistic growth problem. Okay, so the carrying capacity of the environment I'm going to give you is equal to 500. I'm also going to say after 100 days, after 30 days, there are 100 fish, so it's not quite the carrying capacity yet. And initially, I have 20. So I'm going to start with 20. After 30 days, I'm going to have 100. The carrying capacity of the environment is 500. So our equation for logistic growth is P of t is equal to L divided by 1 plus B e to the minus kt. So all we have to do is figure, I give you L equals 500. We have to calculate B and K. And actually, the question is how many after, say, 15 days. So that's what I'm actually, this is stuff I give you. This is what you need to calculate, ultimately. So use the given stuff to calculate all these constants, and once you've got the constants calculated, then you can plug in T and get the answer. So we start first with the initial condition. So we have the carrying capacity divided by 1 plus B e to the negative k times 0. And the initial amount is 20. So this is P of 0, not P of, so we have P of 0 is 500 divided by 1 plus B e to the minus k times 0. So we just have to solve for B, because this e to the 0 is 1. So we get 500 divided by 1 plus B e to the 0, which is 1, equals 20. So we multiply both sides by 1 plus B, multiply it out. Actually, no, we don't multiply it out. We can just divide by 20. So we get 1 plus B equals 500 divided by 20, which is 25, I think. Okay, so let me, 500 divided by 20 is 25. So B equals 24. So our equation P of t is equal to 500. Make sure that was the right carrying capacity. Yeah. So you get 500 divided by 1 plus 24 e to the minus k t. So then we use the second case. We know that P of 30 equals 100. P of 30 equals 100. So we write out our equation on the right-hand side with T of 30 put into the equation. So what do we do now? Well, we're going to multiply both sides by 1 plus 24 e to the minus 30k, and that equals the carrying capacity. So this times that equals that. Then you divide both sides by 100 to get rid of that 100, so you end up with 500 divided by 100, which is 5. Okay, then we subtract 1 from both sides. So you get that. Divide both sides by 24. So 4 divided by 24 is 0.1666. Then you take the natural log of both sides, so you can solve for k. So we take the natural log of the answer, which is negative 1.79. So using the inverse properties of logarithms and exponential, that becomes negative 30k, and therefore k is equal to negative 1.79 divided by negative 30, which is 0.0597. So now we have the entire function defined. So we have carrying capacity of 500, 1 plus 24, e to the minus 0.0597 t. And then finally, we want to find out what is the population after 15 days. It should be somewhere between 20 and 100, because at 0 was 20, 30 was 100. You have to go somewhere. You have to go in between. So P of 30 is that. P of 15. I must have added an extra page in here. Didn't need. Okay, so what I want is P of 15. So you get 500 divided by 1 plus 24 e to the minus 0.0597 times 15. So that's just plugging your stuff in your calculator. 500 divided by the quantity 1 plus 24 times e to the negative 0.0597 times t, which is 15. Make sure I put enough parentheses in there, and I get so I got 46. So did that make sense? Yeah. So it should be between 20 and 146 is there. So the answer is 46. Okay, so that's how those work. Let's say I have a radioactive decay problem for my exponential growth of decay, and the half-life is 2,750 years. And I'm given at 6,000 years, I have 5 milligrams of carbon-14. What is the initial amount and how much is there at 15,000 years? Question mark. So the way it works is you can use this to get your constant k, and then I can use this to find my initial amount. And once I have my k and my initial amount, then I can find it at any time. So let's use C for concentration. So C of t is going to be equal to C0, the initial amount, e to the minus kt. Well, the half-life situation is where the ratio of, so C of 2750 divided by C0 is equal to half. And so that removes this constant, puts it over there, and I end up with minus k times t, which is 2750. years. So just like I did with the logistic growth problem, I take the natural log of both sides. So the natural log of 0.5, I should know that by now. Negative 0.693, yep. Negative 0.693 is equal to negative k times 2750. So k is equal to negative 0.693 divided by negative 2750. 0.693 divided by 2750. And I get 2.52 times 10 to the minus 4. So now I know K. The second thing is I knew that at 6,000 years, so I know C of 6,000 equals 5 milligrams. I'm just going to put it in milligrams, 5. So C of 6,000 is 5. So I don't know what the initial amount is, so that's what I'm going to solve for next. So T is 6,000, so I need to put that in there. So I knew K. I found K from the half-life, and I can use the value at any time in years to find C0. So this one's pretty easy because I don't have to do any weird stuff. I just have to know how to take the exponential. So the exponent e to the negative 2.52 e to the minus 4 times 6,000. Make sure that's in parentheses. And I get this number here evaluated is 0.2204. So C0 is 5 milligrams divided by 0.2204, which is 22.7 milligrams. So since we were at 6,000 years, which is more than the half-life, it should be more than double of this. So it's in the order of what I would expect. So now we have the fully defined equation. The original, so the question of how much did we originally have, we had 22.7 milligrams, so that's C0. And now we can have our fully defined equation. So to find it after 15,000 years, we just plug 15,000 in for T. And so that's just a matter of evaluating it without trying to solve for everything. We already have it solved. So we get that, we multiply by, I keep forgetting the number here, 15,000. 15,000. It should be less than 5, because 5 was at 6,000 years. Okay, so 22.7 times e to the negative 2.52 e to the minus 4 times 15,000, close the parentheses, enter, and so the concentration at 15,000 years is 0.51 milligrams. So that was one answer. The second answer was this one. And then the final thing you need to do is solve a first-order linear differential equation using an integrating factor. So you need to make sure you include all the steps. Of course, you can't write down every possible condition, but so you need to understand the steps and how to get there. So here we are. This is already actually in standard form. So the first thing you would do is put it in standard form if it wasn't already in standard form. The second step is you identify what P of X is. That's this term right in front of the y. Then you calculate the integrating factor. So it's e to the integral of p of x dx. So our p of x is negative 3x squared dx. So in this case, that's just a simple polynomial. So you get e to the negative 3 times x cubed over 3. 3's cancel out. So the integrating factor is x e to the minus x cubed. Then you go back to the original differential equation, multiply the whole thing by the integrating factor. Oh, I was like, something's wrong here, because I can't solve the problem. So this is actually cubed here. So this is cubed. If I had x squared, then I'd end up with something we don't know how to integrate. Okay, oh, this is minus, is that right? Or x is positive. It's positive, yeah, okay. So when we multiply out the left-hand side, we'll get e to the minus x cubed y prime minus 3x squared e to the minus x cubed y is equal to 1. Because e to the negative x cubed times e to the x cubed, you add these two together, you get 0. E to the 0 is 1. So the left-hand side becomes this term, the u of x, the integrating factor, times the other variable, which is y. And you get a whole prime, big prime there. And then you integrate both sides, multiplying by dx. So you get 1 times dx is dx. The integral of this is just e to the minus x cubed times y, and the integral of dx is x. We had an arbitrary constant c, and then to solve for y, you're going to multiply by e to the x cubed. So you multiply this whole thing by e to the positive x cubed. So that, this times that is 1, is e to the 0, which is 1. So you get, you'll get y is equal to x e to the x cubed plus c e to the x cubed. And that's your solution. You could factor out e to the x cubed if you wanted to. You would get e to the x cubed times x plus c. Would be another way of doing it. Now, the only other special case that you might see is where you have something where you have a constant multiplied by 1 over x, and you know, I don't know what the heck's on the right-hand side. Doesn't matter. So there are lots of different cases. Let's say you had that, or you had 2 over x times y. You had y prime is positive 2 over x times y. All these different kinds of combinations. You could have y prime minus 1 over 2x times y. So these all are essentially some constant times 1 over x. So when you actually find the integrating factor, let's just do it for each one of these. You'd have e to the integral of negative 1 over x dx. So you factor out the sign, And you can do that in all the sign and the number. In this case, the number is 1. You end up with this natural log thing. So you'd end up with e to the negative natural log of the absolute value of x. So before you can't use the inverse properties of the logarithms and exponents until you take this sign or the coefficient and the sign inside. So this becomes e to the natural log of the absolute value of x to the minus 1 power. So this negative 1 out front becomes the exponent. So now you can use the inverse properties of logarithms and exponential functions. You can do that. Okay, so that would be the first case. Now, the second case, you would have e to the integral of negative 2 over x dx. So again, you can factor out the negative 2, and you end up with x dx, x dx over x. Again, the integral of dx over x is the natural log of x. Can't use the inverse properties until you move the exponent inside. So in this case, actually I'm just going to keep going down here so you can see all these here. So once it's inside, then you can't. You'd end up with this term here with the exponent, the 2 becoming the exponent. And because you're squaring it, really what you're doing is you move the negative exponent to the denominator, change the sign. When you square it, you can take the absolute value away. So that's that case. Let's say you have a positive p of x. So you would have e to the integral of 2 over x dx. So again, you factor out the 2, end up with your just x over dx, dx over x. So you get e to the 2 times the natural log of the absolute value of x, just like we had up here, except the coefficient out front is positive. You still move it inside. And then you can use the inverse properties of natural logarithms and exponents to do that. And again, you can take the absolute value sign off because you're squaring it. And then the final example I'm doing here is where you have 1/2 times 1 over x, basically. So you get the integral of negative 1 over 2x dx. So you factor out the negative 1/2. So you're again left with dx over x. Integral of dx over x is the natural log of the absolute value of x. Again, you move the exponent, the coefficient into it as a exponent. And then you can use the inverse properties of logarithms. You get the absolute value of x to the minus 1/2, which is 1 over the square root of the absolute value of x. So that's how you do it. So I'm just showing you all the possibilities, but you should hopefully get the gist of what's going on here. If you end up with something with 1 over x times any kind of constant, the constant's going to end up being the exponent once you bring it inside, so that you can use the inverse properties of logarithms and exponents. Okay, so that's it.